All right, so very last thing that we did was talking about calculating the pH of acids and bases. And we did pH calculations for an acid or base that it was a strong acid, which ionizes completely, or a strong base, which is ionic, therefore dissociates. And so you can find the concentration of the hydronium ion from the strong acid and calculate pH directly from that, calculate the concentration of the hydroxide ion from a strong base, calculate pOH, subtract from 14 to get the pH of a strong base. And we were just starting to talk about weak acids. Weak acids only ionize to a small degree, so they end up, rather than going to completion, they go to equilibrium, which means to find the concentration of that hydronium ion at the end is an ice table, just like we did in chapter 15 for the equilibrium tables. So we had stopped just before we did this practice problem, and this practice problem you're following along on the book is on page 737, sample problem 1612. So the question says the Ka, remember uppercase K is equilibrium constant, so this is the same as the equilibrium constants we had in chapter 15, that A just represents that it's for a weak acid, of hypochlorous acid, which is HClO, one of the weak acids, is 3.5 times 10 to the negative 8. Calculate the pH of a solution at 25 degrees Celsius that is 0.0075 molar in HClO. So we said that because this is going to be at equilibrium, you're going to need an ice table. We've gone ahead and started the ice table. All of the ice tables for these weak acids are going to look generally the same, meaning you're going to have some sort of a weak acid that has a hydrogen. So you can write this just as HA. Why are we not? Why is it not loading? Hang on. So once we have our ice table constructed, we can go ahead and write out our equilibrium expression. So in this case, our equilibrium expression is going to be equal to the concentration of the products over the concentration of the reactants. That's the light blue. So our products are going to be X and X, so we'll end up with X squared on the top. Really? Come on. Come on.
There's a button.
That's going back. No, I don't. Oh. Technical difficulties. All right, so since X and X are your two products, you'll end up with X squared on the top. On the bottom is your reactant, so that's just the 0.0075 or whatever your initial concentration is, minus X, and of course we ignore water because it is a liquid. Plug in our K value. Our K value was given. If it's not given, you would check that table of weak acids on page 735. Times 10 to the negative 8. So we're going to start off by making the assumption that X is small to make our math easier, which means we're going to ignore the minus X. You can't ignore all the X's if you assume X is small because, of course, really small numbers, when you multiply by them, have a big effect on the answer. But subtracting or adding small numbers does not have a big effect on the answer. So when we assume X is small, then we have a perfect square root, and we can take the square root of both sides. So when we take a square root, the numerator, X squared, square root of it's just X, and on the bottom, the square root of the 0.0075. That is 0.0866. On the other side, square root of our Ka gives us 1.87 times 10 to the negative 4th. bring the denominator out front to get rid of it. And we end up with x is equal to 1.62 times 10 to the negative fifth. As our x. So before we go any further, let's check and see if that was a good assumption by finding the percent ionization. So I'll just start a clean slide so we have some space here. So percent ionization is how much it ionized divided by your initial concentration times 100%. So in this case, it ionized by X amount, that 1.62 times 10 to the negative fifth. Divided by your initial starting concentration, which for this problem was 0.0075. And then times 100 to make it a percentage. And we get, in this case, a percent ionization of 0.22. Which is definitely much less than 5%, which means the assuming x was small is a good assumption. You do not have to go back into the quadratic. So the original question is find the pH. So again, pH is equal to the negative log of hydronium. Hydronium ion concentration from our table is equal to x, so we're just going to plug in what we found for x. And what do we get for the pH of this? By the way, this is an acidic solution, so we're expecting the pH to be less than 7. Make sure your answer makes sense. It's the negative log of 1.62 times 10 to the negative fifth. We're going to do 4.79. Yep, 4.79. So your final answer is 4.79. Which makes sense. It's a weak acid, so you don't expect the pH to be extremely small, but it is an acid, so we do expect less than 7. So a pH of 4.79. Less than 7 is an acid, but not incredibly tiny small, like 1 or 2, like you would expect for a strong acid. So, any questions? All right. So, percent ionization, as we just saw, you can calculate the percent ionization to determine whether or not your assumption was a good assumption. As long as it's less than 5%, then it's a good assumption. As we learned last semester when we were talking about electrolyte solutions, as you increase the concentration of a weak electrolyte, it is going to ionize less than if you lower the concentration. And the reason for this is basically Le Chatelier's principle. If I'm looking at the ionization of an acid, and I'm just going to use the general format of a weak acid, HA plus water is at equilibrium with my hydronium ion and my whatever leftover conjugate bases. If I'm increasing the concentration, what is that doing to my equilibrium? Am I removing a species or adding a species? Let's talk about maybe Decreasing the concentration. If you're decreasing the concentration, that means you're removing what? Or adding something. If I wanted to decrease the concentration of something, dilute it, what would I add? Water. So let's say decreasing the concentration, diluting it by adding water. That means I'm increasing the water. So if I increase the water, that will drive the equilibrium in which direction? Forward or backwards? Forward. Good. So if that drives the equilibrium forward, is that making more ions or less ions? More ions. Good, because driving it forward is driving it to the side that I have ions. So decreasing the concentration, diluting it by adding more water, drives it to a higher percent ionization. So that's why down here where you have low concentrations, you have high ionization. As the concentration increases, the ionization decreases. Because as you increase the concentration, you're removing water or lowering that reactant of water, which is going to drive the reaction backwards, back towards the non-ionized species, just the acid, molecular acid. Because of this, we can use this to kind of estimate when it might be a good idea to use that assumption of X being small or X being large. If I have a high percent ionization, can I assume X is small and ignore it? No, I can only make that assumption if my ionization is less than 5%. So at low concentrations, your percent ionization is high, and you cannot make that assumption. Of course, since the quadratic is time-consuming for most people, if you want to just go ahead and make that assumption and then check the percent ionization later, you can go ahead and do that. So here's the question. Determine the pH and percent ionization for acetic acid solutions with the following concentrations: 0.15, 0.015, and 0.0015 molar. So this question is asking us to do the ice table and find out what the pH is, but really also to find out what the percent ionization is, and how, as we decrease the concentration, our percent ionization is going to change, and see if at some point it gets to the point where the concentration is so low that the percent ionization is so high that we end up with greater than 5% ionization, meaning we have to go back and do the quadratic. So in the interest of time, I'll just show you how this would be worked out. We do our ice tables. So the first one is the ice table for the 0.15%, exactly the same as the last problem. Plug that in to our equilibrium expression, solve for X. In this case, we got a percent ionization of 1.1%. So is assuming X is small a good assumption? Yes, it was a good assumption for the 0.15. We redo the table with 0.015, and we get a percent ionization of 3.5%. Is it still a good assumption? Yes. We redo the table again with 0.0015 molar. Now we get 11% ionization. Still a good assumption? No. So in that case of C, what should you do when you see that you got a percent ionization greater than 5? Go back, put the minus X back in the denominator, and do the quadratic. Good. All right, any questions about that? Most of the time it'll turn out you'll have less than 5%, you'll be good to go. All right, so you can also do this backwards, just like we do any other problem, forwards, backwards, finding density or using density to find volume, something like that. We can also do an ice table backwards to find out what the Ka of a weak acid is. So if I had an acid that I don't know what it is, and I want to find out what the Ka of this acid is, I can measure out a specific concentration of this acid, and I can measure its pH using a pH meter fairly easy. So in this question, we're being asked to determine the Ka of a weak acid that we know is 0.15 molar solution, and we've measured that it has a pH of 3.47. So now, when we do our ice table here, we know the pH which if we take the pH concentration of hydronium ion is equal to 10 to the negative pH, so that's the inverse of our pH equation, we can find out what the concentration of hydronium ion is. So we found the concentration of hydronium ion in this case is 3.39 times 10 to the negative fourth molar. If that's our concentration of hydronium ion that goes in our table, then that means that must be our X. So we can fill out the rest of the table. If this is plus X and plus X, this must be minus X. We have our starting concentration of our weak acid was 0.25 molar, minus what we found X to be gives us our final concentration of the acid, or our concentration at equilibrium. At this point in time, it's going back to a chapter 15 questions. Given these concentrations at equilibrium, what is your equilibrium constant? So you're going to write your equilibrium expression. It's equal to the products divided by our reactants. So there's our products, and they're both the same, so it's just going to be squared. Divided by our reactant on the bottom. Solve for it, and there's our Ka of this acid.
Where did you get the 3.9 times 10 to the negative 4?
So if we're given the pH is, where are we? Given the pH is 3.47, and pH can be solved, or pH can be used to solve hydronium ions by taking the inverse of the pH equation. So the inverse of the pH equation is concentration of hydronium is equal to 10 to the negative pH. So 10 to the negative 3.47 is that 3.39 times 10 to the negative fourth. So this is honestly even easier because you don't have to do any algebra. Ready to try one? All right, let's try a sample problem. You got it?
So that 0.2497, you got that from subtracting 3.39 from that?
Yep. So this minus that is where that came from. Equals. So. All right, let's find the pH of a weak acid. So we are on page 742, and that's where this practice problem was. Now let's do the sample problem on that same page. Aspirin, acetyl salicylic acid, is a weak acid. It ionizes in water according to the following equation. Now, even if I didn't give you that equation, if you look at the formula for aspirin, to make this its conjugate base, what do we change about the formula for aspirin to make it its conjugate base? Good. Take off the lone hydrogen. So even if I didn't give you the equation, you could still write the equation. All you know is you're just taking off that hydrogen that's out there by itself at equilibrium with hydronium. All right. So the question is, a 0.1 molar aqueous solution of aspirin has a pH of 2.27 at 25 degrees Celsius. Determine the Ka of aspirin. So go ahead and use the method we just used and see if you can find the Ka of aspirin. So I start off by using that pH to find out what your concentration of hydronium is. Anybody stuck? Need some help? Anybody got an answer? Good. 3.05, or we're just going to go 3.0 because we've got two sig figs, times 10 to the negative fourth. So we find the concentration of hydronium by inversing the pH equation, plugging the pH we're given. The concentration of hydronium ion is our X. So when we make our ice table, our X line is that 5.37 times 10 to the negative 3. Plug in the initial concentration minus that X will give us the equilibrium concentration of our original acid. And then we have our hydronium and the conjugate base are going to be the same because they're both X. Plug that into our equilibrium expression, concentration of products over concentration of reactants. Plug that in and you get 3.0 times 10 to the negative fourth for your equilibrium constant. Any questions? So section 6 was all about calculating the pH of a weak acid. So what do you think the next section is? Weak base, calculating the concentration of a weak base. So this sample problem here, if you're still copying it down, is on page 743. We're going to move on to the next section now. So next one, calculating the concentration of a weak base. Weak bases are molecular, and just like a weak acid, they're going to ionize in water at some sort of equilibrium rather than going to completion like a strong acid would or a strong base, which dissociates completely. So we're going to have a general format for what those equilibrium reactions look like, just like we had for the acid. So the acid, again, was the HA plus water equals hydronium, H3O plus your conjugate base, A minus. Now, B is going to stand for whatever your base is. It reacts with water. Now, because a base is a proton acceptor, it's going to pull a hydrogen from the water, and the base is going to turn into hydrogen hydrogen plus the base, so you end up with HB with a positive charge. While water, once it loses one of its hydrogens, you're left with hydroxide OH minus. So that's the general format of any of these. If your base is, for example, ammonia, NH3 plus H2O would be at equilibrium with add another hydrogen to ammonia, and you get NH4 with a positive charge, and then water becomes hydroxide. Your equilibrium expression, still concentration of products over concentration of reactants, and we're still ignoring the water because it's a liquid. So it's going to be your conjugate acid of your base. Remember, to find conjugate acid, you just add a hydrogen and increase the charge by 1, times the hydroxide, divided by your concentration of your base at equilibrium. Now, this is going to be equal to your equilibrium constant K, and because we're now dealing with a base instead of an acid, we have a B instead of an A, but it's still just the equilibrium constant calculated the exact same way. But we're just dealing with bases, so we'll have a new table. So on page 744 is the table of common weak bases, just like we had one for the weak acids and their K values. So right there is ammonia. Ammonia has a Kb value of 1.8 times 10 to the negative fifth. We also have ethylamine, methylamine, pyridine, and this is cutting off the bottom half of the table, aniline and urea, which is misspelled on this slide, but is correctly spelled in your textbook for some reason. It should be EA, urea. I don't know why it's spelled that way, but maybe that's the spelling in Britain, I don't know. Urea. Now, as for finding the pH, it's the exact same thing we did with the acids. We're going to write that equilibrium expression or equilibrium reaction. We're going to construct an ice table, and we're going to solve for X, the exact same way we did with the acids. The difference is, with weak acids, X was equal to the concentration of hydronium, H3O+. So finding the pH was as simple as just taking the negative log of X. Now, in your equilibrium expression, instead of making hydronium, we make hydroxide. Can you still find pH from hydroxide? Yep, it'll give you the POH. So the negative log of that will give you POH. So in the very end, what do you have to do to find pH? Good, subtract from 14. So that'll be your last step, is subtracting from 14. But other than that, it's the same steps, just at the very end you subtract from 14. So let's try out this sample problem, still on page 744, 745. The question is, what is the pH of a 0.040 molar solution of ammonia? So again, we're going to construct our ice table. So ammonia plus water makes ammonium and hydroxide. We are given our starting concentration of ammonia, minus X plus X plus X, ignoring the water. Starting concentration minus X, X and X. When we write our equilibrium expression, it's going to be the products, both are X, divided by the reactants, set it equal to our Kb. Now, this problem did not tell us what the Kb is, so where did this 1.8 times 10 to the negative fifth come from? The table, right? Right there. 1.8 times 10 to the negative fifth is the Kb for ammonia. So at this point, what should we do to make our lives easier? Just what? Try and shorten how? Good. Take out the minus X. We're going to assume X is small, just like we did with the acids to avoid the quadratic. Assume X is small, which then we can take the square root of both sides. So square root of X times X is just X. Square root of 0.040 is 0.2. I should have known that. 2, 0. And square root of 1.8 times 10 to the negative fifth, 0.00424. Bring the 0.2 out. And we end up with 8.49 times 10 to the negative fourth for our X. So if that's X, that is equal to our concentration of ammonium and hydroxide. 9 times 10 to the negative fourth. So at this point, if we take the negative log of that, it will give us what? pH or POH? POH, good. So the POH is equal to the negative log of 8.49 times 10 to the negative fourth. And that gives us a POH value of 3.07. Which means, what is our pH? Good, 10.93, or 14 minus 3.0. And there's your final answer, 10.93. Now, urea is a weak base, or sorry, this is ammonia. Ammonia is a weak base, so would we expect the pH to be less than 7 or greater than 7? Greater than 7. So 10.93 is greater than 7. Make sure, again, your answer makes sense. So I'm dealing with a weak base. I expect my pH to be greater than 7. And sure enough, it is. Questions about how we did that one? All right, so just like we did with the last one, with the acids, you can also use the pH to find the Kb of an acid. Exact same thing. So let's just look at this problem. Caffeine. Caffeine is a stimulant found in coffee or tea or some other substances. It's a weak base. It ionizes in water according to the following equation. So again, even though I didn't give you this equation, to find the conjugate acid of a base, what do? Good. Add a hydrogen and increase the charge by 1, or in this case, go from neutral to +1. And then you're left with hydroxide from the water. A 0.15 molar solution of caffeine at 25 degrees Celsius has a pH of 8.45. Determine the Kb of caffeine. So we're going to do what we just did, but in reverse. So if this is my pH, then that if I take 10 to the negative that, will that give me concentration of hydroxide that I can put in my ice table? No. So before I do anything else, what should I do with this 8.45 pH? Good. Subtract it from 14 to make it a POH. So if that's pH, then my POH is 14 minus that. It's 5.55. Now, if I inverse my POH equation, I get that the concentration of hydroxide is equal to 10 to the negative POH. So concentration of hydroxide ion is 10 to the negative 5.55, which is 2.82 times 10 to the negative 6. And that's my X in the ice table. Now can you solve for K? When we plug that value of X into our ice table, notice that our starting concentration of caffeine was 0.15. When we subtract off what we found for X, our value is still 0.15. Why is that? It's so small. If you plug into your calculator 0.15 minus 2.82 times 10 to the negative 6, you will get 0.149997, which rounds to 0.15, which means that this has a very low percent ionization. If we were doing this reaction forward and finding x, it would have been a very good assumption to assume that x is small, and we can ignore that minus x. Plug into your equilibrium expression, and you'll get a Kb value of 5.3 times 10 to the negative 11, which is a very low K value compared to those other weak bases. So low K values means the reaction did not occur very much in the forward direction, meaning your percent ionization is going to be very small. So that minus x, ignoring it, is probably a very good assumption. Any questions about weak bases, or we feel good about them? Good. All right. Already in section 7. So we learned earlier how to write the conjugate acid or conjugate base. So writing the conjugate base of an acid, you remove a hydrogen. Writing the conjugate acid of a base, you just add a hydrogen. Now we're going to talk about the relative strengths of those and what the relationship is between the Ka and Kb when you're dealing with conjugate acid-base pairs. So, for example, let's look first at a strong acid, HCl. HCl is a strong acid, so it ionizes completely, so this reaction arrow is going one way, not at equilibrium. So if the reaction is one way, that means the reverse reaction would not occur. So the chloride ion, which is the conjugate base of hydrochloric acid, would not react with water to make HCl and hydroxide. So in this case, chloride ion, which is the conjugate base of a strong acid, HCl, is what we would call a weak conjugate base. Now, when we talk about weak conjugates versus strong conjugates, the term strong conjugate does not have anything to do with a strong acid or base. It just means that it is strong enough to affect the pH, but it does not mean like it's a strong acid. If I say something's a strong conjugate acid, that is nowhere near as strong as a strong acid. That just means it is strong enough to at least affect the pH. So by weak conjugate base, that means that it does not react with water enough to make any hydroxide, therefore it cannot affect the pH. So weak conjugates cannot affect pH. And here is the rule. The conjugate and this is a base. Conjugate base of a strong acid is a weak conjugate base. The conjugate base of a strong acid is going to be a weak conjugate base. Now let's look at a weak acid. So hydrofluoric acid is a weak acid, meaning that its reaction is reversible. Because its reaction is reversible, that means that its conjugate base, which is the fluoride ion, can react with water to make hydroxide. If it can react with water to make hydroxide, can it have any effect on pH? Yes, because pH is affected by hydronium or hydroxide. So if fluoride ion can make hydroxide by itself, then it's going to affect the pH. So here's the rule now. The conjugate of a weak acid is going to be a strong conjugate base. So a strong conjugate base. Again, this is nowhere near on the level of an actual strong base. This is not going to, ionize completely with water to make a whole bunch of hydroxide and make ourselves a basic solution. It is just strong enough to affect pH. So this term strong is relative. Relative to other conjugates, it's relatively strong, at least strong enough to affect pH. Same rule, same pattern applies for bases. The conjugate of a strong base is a weak conjugate acid. The conjugate of a weak base is a strong conjugate acid. Same rules apply. And we're on page 747. On page 747, and this is color-coded on page 747 to make it a little bit easier to follow. If your acid is strong, then its conjugate base will be weak. If your acid is weak, its conjugate base will be strong. Again, at least strong enough to affect pH, but still not an actual strong base, a strong conjugate. For bases, a strong base will have a weak conjugate acid. A weak base will have a strong conjugate acid. This is on page 747. And it's a little bit easier to follow on page 747 because they color-coded it. But just think opposites. If it's a strong acid, it's got a weak conjugate. If it's a weak base, it's got a strong conjugate. All right. So if we have the conjugate base of a weak acid that is strong enough to affect the pH. If it's strong enough to affect the pH, then it's going to have its own Kb. So how do we find the Kb of something like that? For example, when we had here fluoride ion we said was a strong conjugate base. Now, fluoride ion, you're not going to find that in the table of weak bases because strong conjugate bases are still weaker than actual weak bases because it's just a conjugate base. It's not a full-on base. So its Kb is going to be very, very small. So you're not going to find it in a table. We're going to have to calculate it from the Ka of the acid we started off with. So next we're going to talk about what is the relationship between the Ka and the Kb when you're dealing with the conjugate acid-base pair. So let's write this out for a weak acid. So this is acetic acid, CH3COOH. Again, the hydrogen on the end there is our acidic proton, so that's the thing that gets lost when we become the conjugate base. So this is the acetate ion. Acetate ion, which is the same thing that back in chapter 2 we gave the formula C2H3O2 minus. From our table of polyatomic ions, exact same thing is just written in the order that it would be structurally, but same ion. So if I wrote the Ka, the equilibrium expression for this, it would be hydronium, H3O plus, over times the acetate ion divided by the original acid. Now, because this is a weak acid, acetic acid is a weak acid, then acetate is a what conjugate base? Strong conjugate base, good. So if it is a strong conjugate base, that means it can act as a base. So acting as a base means when it reacts with water, it produces what? Hydroxide, good. So when this acts as a base, its equation will look like this. It reacts with water to make hydroxide. Now, because it's acting as a base is a proton acceptor, that means it pulls a proton off of the water. So when it pulls a proton off, acetate turns back into acetic acid.
So how do you know that the top one is a strong conjugate again?
So because we know acetic acid is a weak acid. We know acetic acid is a weak acid because it's not one of the 7 strong ones. Therefore, acetate must be a strong conjugate base. So we can write its equilibrium expression, again, the concentration of the products over the concentration of the reactants. So now we have these two equations and their two K's. Ka for acetic acid, we can find that in a table. We go back to the table chapter page 735 was the table for the Ka's of weak acids, and for acetic acid, Ka is 1.8 times 10 to the negative fifth. So we know what the Ka for acetic acid is. We want to know now what is the Kb for its conjugate base. That's what we're trying to find right here. What is the Kb of its conjugate base? So taking these two equations and adding them together. So chapter 15, when you add two equations, what do you do with their K values? Multiply them. Good. When you add two equations, you multiply their K values. That's what we learned in chapter 15. So when we add these two together, we end up with the equation H2O is in equilibrium with hydronium and hydroxide, because the acetic acids will cancel, the acetates will cancel. This is what we are left with. This is the equation for the autoionization of water. Of water. What did it do? So the autoionization of water has a K value, Kw, of what at 25 degrees Celsius? What's the K of water at room temperature? Good. 1 times 10 to the negative 14. This is true for any conjugate acid-base pair that you end up with a strong acid or base. Won't happen if you have a strong acid, weak conjugate base, because the reverse equation doesn't happen at all. But if you have a weak acid, strong conjugate base, or a weak base, strong conjugate acid, you will end up, when you add their two equations together, with the autoionization of water, which we know the K value for that. So if we know the K value for your final equation, and you know the K value of your acid, can you find Kb? Yes. Ka times Kb must be equal to Kw, because when you add two equations together, you multiply their equilibrium constants from chapter 15. Kw at room temperature is 1.0 times 10 to the negative 14. Ka and Kb, we can look up in the tables and solve for whichever one is unknown. So in the case of our acetic acid, we knew that Ka was 1.8 times 10 to the negative fifth. So let's find the Kb of acetate. What is the Kb for our acetate ion? We're expecting it to be a small number, significantly smaller than we had with most of the weak bases, because again, it is a strong conjugate base, but that is relative to other conjugates. It's still weaker than most weak bases. So what do we get for Kb? Good. 5.6. Yeah, 5.6 times 10 to the negative 10. So in this sample problem, we just did part A, determine Kb for acetate. We just did that.
So like, with that, would you go with the equation
I'll just give you like this. What is the Kb for acetate ion? So it's up to you to go, okay, acetate is the conjugate of acetic acid. Or for the next one, find the Ka of the methyl ammonium ion. Methyl ammonium has a positive charge. So is that a conjugate acid or a conjugate base? Which one gave us a positive charge when we made a conjugate acid or we made a conjugate base? When we started with a base and made a conjugate acid, because when you start with a base, you add H plus to it to make its conjugate acid. So this is a conjugate acid of the weak base. And what would be the formula for the weak base it came from? What would be different about its formula? If I have an acid, how do I get back to its conjugate base? Do I add a hydrogen or remove a hydrogen? Remove a hydrogen, right? Bases accept hydrogen. So if we're going backwards, we should take off a hydrogen. Should we take off one of the first hydrogens or one of the second hydrogens? One of the hydrogens attached to the carbon and one of the hydrogens attached to the nitrogen. When we were looking at molecular bases, what told us it was a base? It ended in a what? NH, not necessarily NH3, but NH something. It ended in an amine group because nitrogens like to accept and like to accept extra hydrogens. That makes them very good bases because a base is something that accepts hydrogen. So if we're going in reverse, are we taking away a hydrogen from the nitrogen or from the carbon? 50-50 here. From the nitrogen. We're going to take away one of the hydrogens from the nitrogen. So CH3 is still going to be CH3, but now how many hydrogens are going to be on that nitrogen? 2. So it's going to be NH2. Do I still have a charge? If I took away an H+, what happens to my charge? Goes away. Good. So we have no charge. So CH3, NH2, even if you didn't know what that was called, by the way, that is methyl ammonia, you could look at the table of KBs, back here. CH3NH2 is methylamine, right there. What's useful from this table that we need to answer the question? KB. So the KB in this table is 4.4 times 10 to the negative 4th. So if that's the KB of the base, no. What did I just say? 4.4 times 10 to the negative 4th. Is the KB of methylamine. How would I find Ka of the methyl ammonium? Good. Divide Kw by the Kb. So Ka is Kw divided by Kb, because as we saw in the last one, Ka times Kb equals Kw. So the Ka of methyl ammonium would be 1.0 times 10 to the negative 14 divided by the Kb of methylamine, 4.4 times 10 to the negative 4th. So what does that give us? Getting 2.3 times 10 to the negative 11.
Okay. So I guess I'm just confused on how we wrote here that was a conjugate acid and you would find the weak base.
Okay, so good rule of thumb is if it has a negative charge, then it is the conjugate base of an acid. If it has a positive charge, it must be the conjugate acid of a base.
So it's always going to be a conjugate something.
Yep.
We're going to be looking, oh, okay.
Yeah, whenever you see something charged, it's going to be the conjugate of something.
Oh, okay.
Yeah. And to get between conjugates, you're just adding or removing hydrogens. If you're already positively charged, you're not going to want to add another hydrogen because you're already positive and hydrogens are positive. So you know you want to take away a hydrogen. If you're starting off negatively charged, like the acetate ion, you're going to want to accept a hydrogen, and that will make its conjugate acid.
What did you say, positive charge?
If you start off with a positive charge, you're going to want to take away a hydrogen. A positively charged thing is the conjugate acid of a base. And you want to find that base, you take away a hydrogen. All right, so next time we will use this concept to figure out what the pH is for salt solutions.